Good morning, St. Philip's Academy. Happy to see you today. Or actually, it's afternoon for you. Where we are, me and Miss Valerie, it's actually the morning. We're still drinking our coffee here. But for you, it's already the afternoon, and you've probably already even had lunch. Well, it is lovely, lovely to see you again. Today, I'm bringing to you your mission specialist. Her name is Miss Valerie Casasanto, and she is going to tell you all about the mission that all of you are going to be mission specialists for. And that is called the ICESat-2 mission. So in the next half an hour, by the end of the half an hour, you're going to know so much about this really, really cool satellite that's going over the UK, over Europe, over everywhere, all over the entire planet, and helping us better understand our home planet. So give me a thumbs up if you're ready for that today. All right, we got thumbs up. I'm loving it. Then without further ado, my dear friend and colleague, Miss Valerie Casasanto.
Hi, everyone. I'm so happy to see you all, and I really appreciate you listening to the presentation. And I want you to know that there will be ways for you to interact because I have lots of questions for you. And I hope that you will listen and participate and answer any questions that you know the answer to, or even guess the answer to. So with that, let me share my screen here so that you can see my presentation. I have lots of animations and graphics and visualizations.
Looking perfect.
Okay, great. So I work on the Ice Cloud and Land Elevation Satellite 2, or ICESat-2. And you see down here, our logo includes a penguin.
Sorry, we can't see your screen.
Pardon
Sorry
me?
to interrupt. We can't see your screen. It's just black for us.
Oh,
Let's wait a moment.
Huh, I can see it on my end. That's interesting.
I wonder if they come out and go back in again, or let me try another slide. Do you see that one?
No, not at the moment.
Oh, interesting. Or I wonder if maybe since you and I can see it, Valerie, I'm wondering if maybe it's something that they should come back in and out and in again. This is
Or maybe make them a presenter, or
yeah, let's do that. Let me do that and just see if that helps. I'm going to make them co-host. We'll try anything. You know how it is, folks. You lived through COVID. You know, technology, sometimes it's amazing and sometimes it's rather frustrating. Let's see if this makes any difference. And why don't you stop sharing and then start sharing again? We'll try that.
it's a good idea. Let me do that.
Any luck now?
See it now?
Yes, we can see.
Good.
Ooh, all right. Thank you, folks. All right, as you were, my dear.
That's called troubleshooting. And you know what? Astronauts do it all the time in space. And they keep with them duct tape. Do you know what duct tape is? Anyone know what that is? It's really strong. Okay, yes, I see a hand in the back.
Henry, what do you think it is? Really strong tape. Yeah.
Right, yeah. So because astronauts in space, guess what? Stuff doesn't stay put like here on the Earth on the table. Everything will float around unless they tape it down. So anyway, that was a side diversion. So back to the ICESat-2. So what do you think ICESat-2 studies? Any guesses out there?
Put my hands up.
On the planet Earth.
Sorry. The weather we've had.
Okay, well, we shall see. So here we go. First of all, I wanted to introduce myself, and I have where I live on a Landsat, that's another mission that studies the land, image behind me of the Chesapeake Bay. It is one of the world's largest estuaries and is located on the northeast coast here where the red dot is. And the red dot covers a lot, but basically it's a giant bay that goes out into the Atlantic Ocean off the coast of North America. We're between New York and let's say North Carolina here. And personal note, I live on my sailboat, most of the year. And this is me sailing yesterday, believe it or not. We had beautiful weather. And this is me and my dog Lightning. And this is me working at what I do on my job at NASA. I do education and outreach for the ICESat-2 mission. So I develop experiments and hands-on activities and all kinds of different ways to let children and the public know about what the satellite is doing up there in space and why it's important. So here's a cartoon of the satellite. This was actually done by art students that we collaborated with that I'll tell you about later. And the satellite is currently in space at about 482 kilometers above us, orbiting the Earth using green lasers, believe it or not, to measure the height of our planet. So how thick things are on the planet, like ice, land, water, and even trees and even clouds, which has something to do with the weather. So here is how the
10,
satellite launched
9,
in space.
8, 7, 6, 5, 4, 3, 2, 1. Liftoff of the final Delta II, launching nearly 3 decades of science research and exploration missions, lifting ICESat-2 on a quest to explore the polar ice sheets of our constantly changing home planet.
So our satellite launched 6 years ago in 2018. And this is a cartoon now. What you just saw was an actual video of the rocket launching with our satellite aboard. ICESat-2 goes out into space. Once it hits orbit, then the space fairing opens, the satellite comes out, and you will see another animation of that
Plus
next.
46 seconds, max Q, maximum dynamic pressure.
It only takes like a couple of maybe 10 minutes or so. It's not long at all.
And 57
Get
seconds
out
in,
into
we have
orbit.
wet burnout on the
And here's a conceptual animation, as they say. And this is what happens once the satellite gets ejected into orbit. Then the solar panel, the purple foldable thing that's unfurling, is a solar panel. That's the power for the satellite, how it can do all of the stuff it does. And basically what happens, I'm going to rewind it so I can tell you what happens again. So basically it's all folded up like an origami, and so it can fit inside the rocket. And then once it's up there, the solar panel is really big. It's the size of an American school bus. I don't know if you've ever seen an American school bus, but it's like a big orange bus, so it's pretty big. And the actual satellite part is really the size of a smart car, if you've ever seen a smart car. And basically the laser, there's a laser inside of here. It's called the Advanced Topographic Laser Altimeter System. And that's a big acronym. And basically all it is basically like a laser, even like you've seen a laser pointer. And there's one laser and there's a beam splitter, and it splits it into 6 beams so that we can have more coverage on the Earth. And it's a really cool satellite. So basically, as the lasers come out of the little pinhole, and I'll stop it where the laser beams are coming out. Let me see here. Okay, the door opens. Why is there a door? The door is there to protect this telescope here. This telescope captures the photons of light, which you will find out about shortly. And then as the laser pulses, oops, okay, there we go. I didn't hit the pause button. So the laser pulses 10,000 pulses per second. And what that means is when you blink your eye, so if you blink your eye, in the time it takes you to blink your eye, it's about a half of a second. The satellite sends out, fires its laser 5,000 times and collects 30,000 measurements of the height of the Earth in just the blink of an eye. So it's pretty amazing technology, really cool technology, and it's able to get a lot of measurements and very precise measurements. As a side note, the laser beams are not dangerous. They are very weak beams, and they're all safe for animals and people and even pilots in airplanes that might be closer to the Earth's surface. Now, the ICESat-2 satellite is currently orbiting us, as I said. You see the Earth, and you see those green lines. And basically, it's in what we call a polar orbit. So the poles of the Earth, here's the North Pole here, and down here is the South Pole. And the satellite is orbiting around in the polar direction. As the Earth turns under it, it gets coverage of the whole Earth. So it's taking samples everywhere on the Earth. And as it continues to go around the Earth, as you see, the green lines accumulate. So more and more, you get more coverage. And every 91 days, it does a complete orbit, and it will go over the same exact area every 91 days. So we can get to see what the change is from today and the future. So we can see these changes over time, over the weeks, over the months, and even over years. So we can see how our Earth is changing, how the ice might be melting, and how water levels might be changing. Okay, so how does it work? What is LiDAR? Do we have any guesses out there what LiDAR might be? Oh, I see a hand back.
Olivia, do you want to give it a go?
Do you all know what radar is? Have you heard of radar
Yeah.
or sonar? Does anyone know what sonar is?
Lewis, do you want to see what sonar is? You've forgotten? Okay. Aria?
Radar is around you. Maybe LiDAR is under you.
Maybe LiDAR is under you. Henry, do you want to build on that?
Because radar and that's the one that might be above and down.
Okay, so you think about different directions of it.
Okay, well, good guesses, everybody. Let's see. Basically, the satellite, as we kind of saw the other cartoon of our satellite, sends out pulses of light. See those pulses? They bounce off the surface and they return to the satellite, like you see here. The satellite collects in its telescope the photons that return to the Earth, to the satellite from the Earth. And the photons, which are basically little balls of light, they hit the surface and then they travel back up and their time is counted. I don't have my scuba watch, I misplaced it, but basically there's a big stopwatch, a high-tech stopwatch on board the satellite that measures the time the photon or photons traveled back up to the satellite. So if a photon took a long time to get back up to the satellite, do you think that it's a surface that's higher or lower on the Earth? Any guesses? I see a few hands. I'll
Um,
let our teacher,
Alex,
someone.
you think it's lower, Alex? Yeah.
Great.
Yeah, we think lower.
Think lower. That's right, lower, because it would take a longer time to get from a lower surface on the Earth back up to the satellite. Excellent. Now I'm going to show you a video which really explains it really well, and it also talks about how they measure planetary surfaces as well.
If you wanted to find out how tall mountains are on other planets, how would you do it? If you're on Earth, it's easy. You can take a picture, fly over the mountain, or you can actually go there and measure how high it is. On other planets, it's much more difficult. You might be able to estimate height using shadows, or even take 3D pictures from a satellite. But what if you wanted to know what the mountain looked like as a 3D model? To find out, NASA scientists can use a precise measuring tool called LiDAR. Mounted on a satellite orbiting high above a planet, LiDAR instruments are able to accurately measure the distance between the instrument and the landscape below using laser pulses. To make these measurements, the LiDAR instrument first sends a laser pulse down to the planet's surface. The pulse hits the ground and reflects back to the instrument, where an onboard counter measures the time it took the pulse to make its trip. That gives a precise measurement of the distance between the instrument and the ground with respect to the planet's gravitational center. As the satellite passes over the landscape, the instrument sends out a series of regular pulses. By recording and combining these measurements, scientists can use the instrument to gradually build up a map of the height of the terrain. After many more measurements, the end result is a high-resolution 3D model that scientists can view as if they were actually on the planet, flying over the terrain. They can then study its shape in more detail, looking for clues to the relative ages of craters, the shape of valleys and landscape features, and much more. But LiDAR is far more versatile than simply measuring the shapes of mountains and craters. Earth scientists, for example, use LiDAR to measure the height and density of the Earth's forests. Others use LiDAR to study small changes in the heights of the Earth's major ice caps over time. Still other scientists use LiDAR to study the composition and structure of Earth's atmosphere, as well as the atmosphere of other planets. And they can do all that without ever having to climb a mountain.
Okay. So, oops, I'm going ahead of myself. Get back. So before I go more into how it works and more about the LiDAR, I just wanted to let you know that because you've seen the satellite so far in the animations, we have several tools for you to study and learn more about all the satellite parts and pieces, like the solar panel, like the telescope. And we have an augmented reality visual that I can show you how it works. It's, let's see here. It's basically a poster of the satellite. And when you put your phone or your iPad or whatever, you can see the satellite pop out at you. And then all the different parts and pieces of the satellite are explained so that you can understand all the different parts of it. And I know that one of your tasks is to make a satellite model of one of the satellites or more. I'm not sure, Dorian, you can chime in if I'm getting that wrong, but yes. And the other thing we do have is a satellite paper model, and that's downloadable from our website, and I will provide the link for you all. And that one you can make your own model out of paper, and that's fun. Now, what does ICESat-2 measure actually? It measures our planet Earth. So as you see in this visual, and this was created by art students that we worked with, and it shows the satellite with the laser beams. And as it goes over the Earth, it can measure all different things like mountains, ice, even buildings, and land and water, and even trees. And this is another fun thing that we have, and it's called Biome Buddies. And this was also done in collaboration with art students. and they created all different trading cards, basically, of all the different wildlife that live on the different biomes. Biomes are basically a fancy word that means a type of land or a type of thing on the earth. So ice, grass, land, trees, deserts, water. So here they all are, and there's information on each of the cards. And we will probably be able to send you all, your classroom, a pack of these cards, and so that you can see them and touch them in real life. But I will point out the Osprey, the clouds card, because we are on the Weather Watchers program. How many of you students know what an osprey is? Do you have them in England? Osprey, it looks like this one here, this bird, and it catches fish. Anyway, the osprey is represented here because the osprey flies really high up in the clouds, and our satellite can measure not only the ice, land, trees, and water, it can also measure the clouds, and it can tell us what the clouds are like, what type of cloud, and that can help us inform what the weather might be, maybe even predict what the weather might be. Okay, next question for the class. What are photons?
Olivia?
Photons like the satellite like takes pictures of stuff like in the air.
Okay, takes pictures of things in the air. Lewis, what do you think it is?
A photon is basically a single organism.
A singular organism. Good. And Henry, you build on that. Ball of light bounces back from the Earth to the satellite. Really good answers.
Good. I see some of you are listening very well. That's great. Okay, so I want to have you do a thought experiment before I show the next cartoon. So the satellite releases trillions of photons. That's a huge number, trillion. I don't even know how many that is really. It's so much. It's more than 100. It's more than 1,000. It's more than tens of thousands. It's more than 1,000,000. So it's a lot of photons. So I'm going to ask the class to think about, you don't have to answer it, but think about if the satellite is sending out trillions, not just one like I showed you in the former picture, trillions of photons that bounce off the Earth and come back up to the satellite. How many photons do you think get back to the satellite? Think about that. We can have some guesses now, but if there are no guesses, we can talk about it at the end. So with that, I'm going to show, well, we have some hands there, so we'll let you guys.
Teo, how many do you think are coming back? 5 million are coming back. Spencer?
I'd say
A billion coming back. Jemima? About half of them. That's a good way of doing it, so that you're not just quantifying it. You're saying half of whatever goes. Belle? You think exactly the same amount? Okay, hands down. Let's find out.
Hey, let's find out. I love this one. This was also created by our art students, and I think you might like this one. Let me see. I can push play.
Departure code plus 22A4 to start in 5, 4, 3, 2, 1. Excellent job, Bo. Your time has been recorded. Let's add your data to the point cloud. Ready the next group?
Okay, that's my favorite. That was created by the students to help people understand how it all works. So now that you've seen the video, what do you think? Do you have any changes to your answers about how many photons make it back? See a bunch of hands there.
Crystal,
About half a million.
did it look like 500,000 were coming back on that video? Teo, 1. Archie,
50.
50. Oscar,
17.
17. Okay. So
Great, great, great. All correct. 1, it can be anywhere from 1 to a dozen, 12 photons return. And why so few return when you send out trillions? So the reason is that the photons, when they come down, they get stuck in clouds on the way down, or they bounce off the clouds before they can make it to the earth. They bounce in all crazy directions. Imagine a bunch of bouncy balls coming down and you drop them and then they go in crazy directions. So only those that make it back up are counted. So very, very few. That's why we have to send so many in order to get enough back to get a measurement. Okay, now on to the areas that we measure. So I love this video because one of the NASA scientists who works in the field actually took this video.
Yeah, the wind is still pretty much up and down, so there should be wind at the tide level as well now. Okay, Roger, that really is going. That's what they're trying to do, Robert. Thanks, Eddie.
I think he got bored of the humans. It's going off now. Okay, next question. Where do penguins live?
Olivia, where do penguins live? Antarctica. So everybody else is anyone else familiar where they live? Archie. Forgotten. Amelia.
And then North Pole and South Pole.
And the poles. Okay, let's find.
Let's find out. Let's find out. Great. Okay, here we go. So penguins are in Antarctica, which I heard some or many of you got right, in the South Pole here. And then the polar bears are in the north. Polar bears aren't in Antarctica, only in the North Pole or Arctic here. And this shows you that we have a lot of ice on the earth. So in the North Pole, where there are polar bears, we have ice and we have different types of ice. We have ice on the land here, and we have sea ice, which is frozen ocean water. We have the same thing in the South Pole, in Antarctica, where the penguins live. This light gray area is sea ice, frozen ocean, around the continent of Antarctica, the land ice on top. The ice is formed by snow, many years and many years of snow, and new snow falls on top and compacts it and pushes it down and makes ice. That's how the land ice is formed. The sea ice is formed when the ocean gets really, really cold and the seawater freezes up. So we have 2 different types of ice. Now, here is a visualization showing the ice in the North Pole on the left and the South Pole on your right. So it's going to start to move. This is changes over the years. And as you see, the ice grows and shrinks. It changes, okay? And why do you think it changes? Does anyone have any guesses out there? Let's see.
Changes.
A couple
Alex, what do you think?
Climate change.
Climate change, good. Ellis?
Over the years, it gets hotter and then colder.
Over the year, it gets hotter and colder. The sea temperature is going to change, Olivia.
Global warming.
Global warming as well. Okay.
Okay, great, beautiful. This is showing basically the natural cycle of how the ice naturally shrinks and grows based on the season. So you got it right. And when it gets hotter in summer, it shrinks. And when it gets colder in winter, it grows. But overall, it is decreasing over the years, as you all know about global warming. But this I'll play again a little bit, but basically, this is the natural pattern and it depends on the seasons. And then overall, though, we have the ice is less over the years. So you will see how the animation changes over the years. Now, this is from the 1970s, way before you were born, up until, if you follow the red line, it shows you the year. So this is 1995, 2000. As we increase in years, we have less sea ice. This is just showing the sea ice. This is not showing the change to the land ice. The next one I have does show the change to the land ice. This is a very complex graphic, but just look at this big white blob here. And you see this is Antarctica and the changes in the ice thickness over the years. And where you see orange here, you have thinner ice. And where you have blue, you have thicker ice. And when the ice melts, it runs off into the ocean. Okay, so why do you all think we need to have ice on our planet? Any guesses?
Jemima, why do we need ice?
So the animals that need ice in their habitat can still live.
Absolutely. Animals that have ice in their habitat as part of their habitat can still live. Amelia?
If we didn't have ice, like some animals like probably like the
Mhm.
have ice and it's fine.
Yeah, animals becoming extinct because of it.
Penguins would die.
Aria?
So if we didn't have ice specifically here, it wouldn't be good because it means it could get warmer, and that means sometimes it could disrupt animals like squirrels' hibernation pattern.
Good, it can disrupt hibernation patterns. That's a really good point. Okay.
Yes, wow. We have a really smart class out there. Okay, so the main reason has to do with its color and its shininess. So this one shows us that with the ice being white, bright, and reflective, it reflects off the sun's rays, it reflects off the heat. And if we have less ice and more dark water where the light penetrates the dark and doesn't reflect off, we have more warming. So I think I heard a gal out there say something to that effect, that we would have more warming if we have less ice. So basically, our ice is basically like our cooling system for the planet, and it regulates our climate and also the weather. So the ice helps us in so many ways, even though it's not right here in the United States or the UK. It's in the north and the south, but it really helps us a lot. It's very important. Now, when the ice melts, what do you think happens on the earth? You may have some ideas about that. When the ice melts, and then where does it go?
Aidan, what do you think? What's going to happen if the ice melts?
I think that the warm water will spread and it will get more like hot and warm.
Okay, warm water will spread and it get hotter and warmer. Henry?
I think it will turn to water. So that's why the sea levels will be increasing.
Good. So sea levels are rising because it's melting and turning to water. Alex? Joel?
The sea levels rising, which could cause animals to have to leave their homes and try to find a new one, like refugees or humans.
That's a really good point. Like animals are going to be like refugees because they've got to go and find new habitats. That's a lovely way of putting it.
Wow, fabulous. So many great answers. So, sea level rise, that's the main thing. So if you have ice on the land, and I can't really have a picture, but I'm just showing my hand as a piece of ice, and it goes, or it's my hand is a piece of ice, and it melts off the land and goes into the water. What happens to the water level when you introduce ice into there? It rises, right? Like this graphic is showing the sea level rise. And then when the level rises, people and animals along the coastlines may have to be refugees, like one of you said. So I have one more animation, I think, and a couple more, but we're wrapping up now. I wanted to let you know that the satellite continues to take measurements of the height of the ice and is getting all this information and telling us how it's changing over time. And there are many ways that you students can participate in the mission. There's a tree measurement program where you can compare your tree heights to the satellite measurements. And there are a lot of other ways that you can get involved with our satellite mission. And that not only includes science and technology, but also the arts, which is a super important thing too, because guess what? I could not have explained any of this to you without the arts, without the animations, and without the drawings. So it's super important. So our art collaboration is with college students in Savannah, Georgia, and they came up with Faux the Photon, the character, and a whole bunch of other things that you've seen in the presentation. And this is a little piece about how ICESat-2 measures trees. And that piece featured our penguin mascot, Paige the penguin. And Paige was actually named by students your age in an American classroom. So we're very proud of our penguin mascot. We have activities on our website, and we have a fun zone on our website with interactives and where the satellite model is and other things that you can check out. And you can always email me, have your teacher email me. And with that, I'll say goodbye for now. And if there's any time, I can answer any questions.
And I want to just jump in real quick and just say thank you so much. And also, fifth graders, you have been the most amazing audience, really paying attention for 45 minutes. That's a really long time. We have a hard time getting adults to pay attention for that long. So pat yourself on the back. Good job. As you're learning a little more about this mission and thinking about it, write down questions, brainstorm things you wonder about. You can even take your questions and put them into categories once you have them. And by the way, I got your getting to know me slides. Valerie and I are going to look at them together and we're going to send you some notes on them. So thank you so much for sending them our way. We've been super busy between Valerie was on travel and we had our election and then we both ended up getting sick. So we're now getting better. The election's over. She's back from travel. We'll jump back on. And I want you to be thinking about this really cool mission and thinking of ways that you can make your models out of recyclables and your edible models, and think about how you can do your very short movie and tell people about this satellite mission. So you've already got some great examples of the ways in which art students have worked to learn the science and then find fun ways to help share that with others. That's an important job scientists have. It's not okay to just learn the information. You have to communicate that to others. And sometimes that's the hardest job for some scientists because they're very used to knowing a lot of things about a little. And sometimes it's hard to tell that bigger story. So work together. It's always teamwork. None of this is done by one person alone. And we're just super, super excited to have you and your wonderful, wonderful teacher on board with us. So with that, I will stop. And then if you do have any quick questions for Miss Valerie, I know you probably have things that you've got to move on to. And we're starting our days over here, but we'll continue to be involved and in touch.
Yeah, I've just got 3 questions. Olivia, what did you want to ask?
How long have you been working with the satellites for?
How long have you been working with the satellites for?
Oh, wow. Way before launch. So it's been about 10 years. So, or even 11. So I started way before the launch to work and create all of this and tell people about it even before it launched. Thanks for that great question.
Aria? Oh, what was the date that it launched?
Oh, September 18, 2018. No, I'm sorry. I messed up. September 16, 2018. I'll never forget the date because even though I just did now, because I was lucky enough to be there in California when the rocket launched. It was the most exciting thing in my life, especially because I had worked on the missions and I saw the satellite being built at NASA where I work.
Archie, what's your question? Or how big is the satellite? So we know how big the solar panel is, but how big is the whole satellite? Is that your question?
Oh, okay, yes. So how big the satellite is, let's see if I can do it in metric. Do you all know what the size of an American school bus is? It's like a big bus, like a public bus. The solar panel is that long, and then the actual satellite piece is like a smart car. So it's probably like, let me see, I think it's like 20 feet times 3 for meters, 40 meters long by say 11 meters wide, something like that. But I'll get you the correct answer because I'm just doing the calculation in my head.
And let's take one more question and then we know you can continue to brainstorm and write these down and then we'll get them to you. Yes.
Okay, Jemima, last question.
Was it like really hard to make it?
Was it really hard to make it?
Oh, yes. It took a long time. It took many years and many people and a lot of different types of engineers, electrical, mechanical, and all different types of people were working on the mission. It's super teamwork. And they had a lot of challenges, and they had to build their own stopwatch type of clock that counts individual photons. So that is a real tough thing to do.
So keep thinking about all these wonderful things. And thank you, thank you, thank you. And a huge thank you to your teacher too, because this is a lot of extra work to get involved in something like this. We love you so much. We're so happy you're a part of this amazing project. And we will be in touch with you real soon, okay?
Okay, so everyone says bye. Thank you.
Thank you so much, everybody.